All right, class, yesterday we talked about growth and decay graphs. Now we're going to talk about the models themselves. Growth model, first thing we're going to look at. When a real-life quantity increases by a fixed percent each year or other time period, the amount y of the quantity after t years can be modeled by the equation y equals a times 1 plus r to the t. So a is the initial amount, that's always your starting amount. R is the percent increase in this case, and we express it as a decimal always. This total quantity is called the growth factor, and actually I think I mentioned that yesterday. Okay, decay is the same thing except for it's 1 minus the rate, so it's decreasing by that fixed rate each year. This whole thing is called the decay factor. So that's different than the actual rate, the percent decrease. So let's take a look and see this stuff. The value of a car in thousands of dollars, always read that, that's careful with the units, can be approximated by the model y equals 25 times 0.85 to the t. T is the number of years since cars new. So does it model exponential growth or decay? Well, since the entire growth factor is less than 1, this should be exponential decay. Now, because of that, though, we can't figure out, we have to rewrite it into this form up here to find out the rate. Identify the annual percent increase or decrease in the value of the car. Well, in order to do that, we need to rewrite this. So we need to figure out 1 minus the rate equals 0.85. So hopefully you guys can do that quick math and realize it's 0.15. So this is what it looks like before you combine it to the growth factor of 0.85. And it makes sense. This is the decay factor, actually, not growth, because it's not growing. So every year you only have 85% of the previous year's value is what that's saying. But our actual rate of decrease is that it's decreasing by 15% each year. That's our rate. Okay. Estimate when it'll be 8,000. Be careful. Remember, we are in thousands. So y is equal to 8, not 8,000, because this is 25,000 is the initial amount. Don't just say 8,000. It wouldn't make sense because it's going down and it's starting at 25. So how do we solve these? Well, we either have to get a common base, which we can't do with these weird problems, or we use logarithms, which you don't know how to do yet. So, for right now, just to practice these without knowing how to solve them algebraically, we're going to use our calculator. So just plug this into y1, plug this into y2, and then graph it. When you graph it, I'll get the calculator up for the second one. You have that this is the line y equals 8 here. And then you get a curve that looks like a decay curve. And you get a point that is 7.011, comma, 8. Okay? So, when we get that, that is our answer. So, when is the value 8,000? After 7.011 years. Well, how about this? 7.011 years after buying the car is when it is at $8,000. Okay, so you can't solve those yet until we know how to do logs. So for these problems right now, we're just using the calculator. The things you really have to worry about are the wording, understanding the units, and then going from there. Alright, number 2. Same thing. In 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Right away, I'm going to say, well, that means the rate is 0.0118. That is what you always move the decimal place to convert a percent to a decimal. Write an exponential model given the population in billions t years after 2000. So, y equals, the initial was 6.09 billion times 1 plus the rate to the t, and if we simplify that, we get y is equal to 6.09 times 1.018 to the t. So remember, this whole thing is called the growth factor, whereas this number here is just the percent increase or decrease. Estimate the world population in 2005. So this we can solve because we need to put a t in. Well, if t is 0 is 2000, t of 2005 is t of 5. So we're going to say y equals 6.09 times 1.0118 to the 5th. You type that in, and you get that the world population is about 6.458 billion people. All right, estimate the year. So this is different. I'm not asking when. I want to actually know during which year the population was 7 billion or hit 7 billion. So this is again the same setup as the other one. My population, y, is now 7, and I'm solving for t. Again, we have to use our calculator. This is going to go y1. This is going to go y2. So if I plug that in, I'll show you this one. 7 and 6.09 times 1.0118 to the x. You graph that. There's that. There's that growth. Looks like I might be not in the correct screen. So I'm going to change my window. I'm going to just make my x go from 0 to 20. And I'll make the y go from, I don't know, we don't need to go to 0. Well, we started at 6, so 5 billion to like 8 billion. We'll do that. So we're looking for where it crosses, and there it is, right there. And then you just do second trace 5 to get your point. Enter, enter, enter. And you should get the point 11.871, comma 7. Okay. So I just wanted to go through that again because it's been a while. So we have a graph that looks like this. And there's that piece there. This is 11.871, comma 7. So when I said what year did this happen in, 11 corresponds to 2011. It's not quite at 12 yet, and we don't round this up because it's not, 11.8, you're still in 2011. It might be like October or something, but you're still in 2011. So during 2011 is when that happened. Okay, we got one more problem. This is all about rewriting the problem. Sometimes you'll see radioactive isotopes written like this, where it's 0.5 to the something, which gives, it's kind of like a half-life type thing. But we can rewrite it into the form we've been using today to figure out what the actual percent decrease is, so, or decay. So we have that many grams of chromium-51 remaining after t days is this formula, where A is the initial amount, what's the percent it decays. You can't say 50% because we have this as our exponent. We have to get that back to just t. So we can use our exponent properties and say, well, that's 1 over 28 to the t, because that's the same thing. That's like splitting it apart. If you multiply these, you get back to that. So we can now calculate what is 0.5 to the 1/28th. Well, if you type that into your calculator, you get 0.97554. So that would be the decay factor. That is not the percent it decreases, though. That would be a lot. Remember, we have to set that equal to 1 minus r is equal to 0.97554. So that means that our rate is equal to 0.02445. Okay, so this is what r is, which means that it decays by 2.445% each day. Okay, so we kind of like just took the form and rewrote it back to the form that we were working in earlier. We solved this because we have to have it to just the t. We found the growth factor, or decay factor I should say, and then we found the percent decrease based on that decay factor. Okay, That is all for today. We'll do more of this tomorrow.